All right, this is the second video for section 3.3. So why don't you pause, copy this down, and I'll start chunnering. All right, so I'm going to be talking a lot about that last example we did with the number of hot wings that men ate versus the number of hot wings that women ate. At least 15 men out of 30 in that study, okay? So in that example that we just ran, in the R code, we ran 10 to the 5th minus 1 permutations of who we denoted as M's versus W's. And each time we recorded the test statistic, the average number of wings eaten by the ones we denoted M, minus the average number of wings from the ones we denoted as W, men versus women, okay? All right, we then calculated how many of those 10 to the 5th minus 1 recorded test statistics were greater than or equal to what we observed, that 5.2, okay? Remember, 5.2 was what we observed, that on average, the 15 men ate more than the 15 women, okay? All right, we then defined, or actually we didn't define it, we estimated the p-value as such. And I should just be clear that this isn't the true p-value, this is just our approximate of the p-value, okay? The p-value was the number of times that recorded test statistic was greater than or equal to 5.2 plus 1 divided by n plus 1. And let me just explain where these plus 1s come from. All right, the numerator, we know there's at least one scenario where the test statistic is greater than or equal to 5.2. It was the original data that was given to us, with that designation of men being M's and women being W's led to that test statistic of 5.2. So we know there's at least one permutation that satisfies that inequality. We want to make sure we include it in our count. So I'm going to add 1 to it. And that might mean we've counted it twice if one of our permutations happens to be the original layout of men and women, okay? Fair enough, though. We're going to make sure we count it. So this plus 1 is to ensure that the original data set gets included, okay? And maybe it gets included twice, but at least it gets included. This ensures the numerator is not 0. So it ensures the p-value approximation is not 0, okay? All right. Then in the denominator, since we sort of added one simulation to the numerator by adding plus 1, we're going to make sure we add one simulation to the denominator. Okay. All right. So that's why. And again, as n gets really, really large, capital N versus capital N plus 1, no difference. Essentially no difference. Okay. All right. Now, in general, if we estimate a p-value and it's less than 0.05, then we're going to say that we are going to reject the null hypothesis and say that there's statistically significant evidence supporting the alternate hypothesis. Now, where did 0.05 come from? Kind of arbitrary. It's 0.05 is 1 out of 20. So if it only happens one time out of 20, that seems unlikely that it happened by chance. So we're going to say, okay, something was happening there. But again, if you go out into the real world, maybe your employer will say, look, we want to be really sure. So we're going to have a p-value of 0.01 or 0.005, right? Well, so whatever it is, that's what you work with. All right. But for the most part in this class, we will use 0.05. And if the p-value is greater than or equal to 0.05, then we fail to reject the null hypothesis. So basically we say, look, we can't rule out that the observed test statistic is just as extreme as it is by chance. So we're going to stick with our null hypothesis that the factor has no real impact, and what we saw just happened by chance, okay? So we're going to remain unconvinced that the factor had a real effect. Okay? All right, big fly move. Yeah. Okay. So let me copy down this panel. Hopefully the light's good enough to see. That's pretty good. Okay. So also in that beer wings example in R, we saw the null distribution, okay? So the null distribution is that box plot or histogram provided by R, which lists each and every one of the 10 to the 5th minus 1 values of the test statistic and creates a bar plot, okay? And then if you remember, we put a blue vertical line in where the observed test statistic value was to see how extreme, visually, to see how extreme it was in the distribution. Okay. So the null distribution is provided to us by that box plot in R. And again, it's simply the distribution of all the test statistics under the hypothesis that H naught is true. This differences are just occurring by chance. Okay. Right. So now we're going to start talking about two-sided p-values. So the wings example we did was a one-sided hypothesis test. Okay. Our null hypothesis was that well, I guess this isn't quite the way I wrote it. I should have written mu m minus mu f was equal to 0 versus mu m minus mu f was greater than 0. So it was one-sided because the alternate hypothesis was that the mean of the men was strictly larger than the mean of the women. Okay. In general, we prefer a two-sided hypothesis test, right? Same null hypothesis, but the alternate hypothesis doesn't specify greater than or less than 0. It just says not equal to 0, right? So this allows for the number of wings eaten by the men to be larger than the number of wings eaten by the women, or the number of wings eaten by the men is definitely less than the number of wings eaten by the women. So either way, we just want the opposite of the null hypothesis, okay? So this is called a two-sided hypothesis because it incorporates both the greater than and the less than. Okay? Now, in general, we wish to do a two-sided hypothesis test. It's a more statistically robust conclusion if we can get it, okay? All right, so how do you calculate or compute a two-sided p-value? And we're not really computing the two-sided p-value, we're computing an approximation of a two-sided p-value. Okay? And why is it an approximation? I should have mentioned this earlier. The p-values we're computing are based on simulations that R is doing. And your simulations will yield a different p-value than my simulations were. So none of ours is probably the true p-value. We're just sort of estimating these p-values via simulation. Okay. All right, well, so to compute a two-sided p-value, what we're going to do is we're going to compute two different one-sided p-values. So the first one-sided p-value was the number of times that test statistic, and remember we did it 10 to the 5th minus 1 times, number of times the test statistic was greater than or equal to 5.2 plus 1 divided by n plus 1. That's what we did before. Here's the other side. To be more extreme than 5.2 means we could be 5.2 or higher, or negative 5.2 and lower, sort of like the left end of that histogram. So the other one-sided p-value is the number of times that test statistic is less than or equal to negative 5.2 plus 1 divided by n plus 1. So we're going to have R calculate both of these. And then our answer, our overall p-value, is going to be 2 times the minimum of those one-siders, okay? And in general, we want to do a two-sided test unless there's a clear reason that only one side of the alternate hypothesis is possibly of interest, okay? But in general, we want to say either the factor has no effect or it has some kind of effect, okay? All right, last panel for this video, still in section 3.3. So copy or pause copy. All right, so I'm going to go back to the wings example. There was the null hypothesis. Here's our two-sided alternate hypothesis. The mean of the men does not equal the mean of the women. And our test statistic is the x bar of the m's minus the x bar of the w's. The first p-value we already computed. We already had R computed. And that was 0.00064. And again, your code might be slightly different, right? Now, the second p-value is the number of times that test statistic was less than or equal to negative 5.2 plus 1 over n plus 1. And my simulation yielded 0.00077. And I'll show you how to do this in a minute on R. And so if those were the two one-sided p-values, then our overall p-value is twice the minimum of those two, excuse me. So it's twice the 0.00064, which is 0.00128. And again, it's only an approximate p-value because we got it via simulation, okay? We didn't take all possible permutations. We just took 10 to the 5th minus 1. All right, well, it's still less than 0.05. So in conclusion, we can reject H naught and conclude that there is statistically significant evidence that men and women do not tend to eat the same number of wings. Now you might say, well, I think men eat more. And I said, okay, well, fine. But we know that this factor men versus women, does seem to have an impact on the number of wings eaten. Right. So now let me just crank in the R and show you how we did the other one-sided test. There it is. Okay, so I'm at the same spot I was before. And by the way, bottom right here is again showing us the null distribution. So it's showing me how all 10 to the fifth minus 1 of those statistic values fall between, let's say, -5.5 and +5.5. And there's the blue line showing where our observed test statistic of 5.2 would fit. Okay. All right, so we did the one-sided and we got 0.0064, which I highlight down here. Now, if I go to line 26, this will calculate the other one-sided p-value. So remember, result was a vector that held all capital M values of the test statistic, okay? And sum is going to add up how many of the entries in result are less than or equal to negative that observed value, okay? So we're going to calculate in my result vector of all of those 10 to the fifth minus 1 test statistics, how many of them are less than or equal to negative 5.2. So remember, we defined observed to be 5.2. And add 1 divided by n plus 1. So if I run this, I get that 0.00077 that was up on the board. And just to show you, like, every time we do this, we're probably going to get something different. I can run the simulations starting from line 10 all the way down to line 26. I can run that entire simulation all over again. Again, it's going to take a few seconds. So the bottom left, I'm still not seeing that arrow pointing to the right. And until I do, it's not run through the code. So it's cranking through the permutation test right now. Right, there it is. Okay. And then if I go down to that bottom left, my first one-sided p-value was 0.00079. And the other side was 0.00068. So again, I'm getting different p-value, one-sided p-values each and every time I do this simulation, but they're all ballpark, 0.000, something between 6.5 and 8.8, maybe after that, okay? So we're still getting good statistical evidence that gender does appear to impact the number of wings consumed. All right, and that should do it for this video.